It's my true pleasure to introduce you. Those of you which don't know it, Kevin made some of the very first maps, global maps of science. And then in July 2007, he joined SciTech Strategies to do this full time. Before that, he was with Sandia National Labs. That's how we met. And then at SciTech Strategies, they, as the entire team there, has been working on detailed mapping of the structure and dynamics of science and technology, but also focusing on the accuracy of these maps at the local and the global levels. And also looking at classifications, merging of multiple data types and sources, identification and prediction of emerging topics, but also the development of advanced metrics, which are used and needed by many, many different agencies, but also individuals that need to make decisions. And many of these institutions and individuals, they would love to rank us all and then apply a threshold, and everybody above the threshold gets funded or gets published, and those below don't. And in many cases, it's not so easy to actually make these decisions. It's a multifaceted decision-making process that's going on. And so I hope Kevin can tell us a little bit more about all this work. And I'm just so pleased to have you here. Please take us away.
Okay. And thanks, Kati. Thanks for inviting me. I've wondered really what to do with this time. And so maybe, Kati, you can, is this basically just I talk, or is there interaction capabilities, or basically are the attendees just watching, or can they talk, or what?
So all participants are encouraged to ask questions, but keep in mind that some of them have never seen a science map in their life before.
Okay.
So it's a new audience. Some of the participants came over from the amazing panel that Ryan was hosting, following up on the Intersections series that the National Academy has been putting on recently, which brought together artists and scientists and engineers to talk about how we can innovate together. Some might also still be here because they watched the Science Maps for Kids event, which was right before Liesel's and Todd's presentation of the exhibit itself. And so they might be in the storytelling mode because that's what we did there. We read the comic book. Others might like to understand what a science mapper does. So how does your day unfold? What do you do in the morning, around lunchtime, in the afternoon? How do you end the week? I think that is all part of the discussion. And I'm very happy to ask you all kinds of questions that might come from the audience. But I will also encourage the audience to ask their own questions.
Okay, well, I've got a whole bunch of slides, but what I'll do is I'll kind of pick my way through a few of them, and then hopefully that'll spur some questions, because a discussion Q&A is a whole lot more fun than just plowing through slides. But having said that, I guess I'll get started. So let's see. I need to put this up. All right, so I guess we could call this maybe an introduction to creating and visualizing and accessing global models of science. And I'll talk about global models of science in just a minute. But the first thing I wanted to do is just say that the things that you're going to see here are a team effort. And it's broad in this. This is just the four of us who are at SciTech Strategies. We're a small company that has been doing science mapping for lots of years. We've actually been together as a group. I hired on with Dick about 15 years ago. Before that, I was at Sandia Labs doing science mapping. And of course, many of you, or some of you, will know who Henry Small is. And Henry, he was kind of the right-hand man for Eugene Garfield at ISI, a database provider, literature database provider back 40 and 50 years ago. And he headed up their division that created a number of products, including things like the journal citation reports. And so Henry these days, basically, well, he works half-time. He's retired formally, but works about half-time with us, and pretty much just does what he wants. And that's kind of what we all do. But he's really interested in looking at full text and trying to understand some of the signals that are in full text. Things like understanding what makes a paper a discovery paper, or what makes a paper a methods paper. And so he reads a lot of things and does some machine learning and some other things that ultimately end up in indicators. Mike Paddock is our computer guru, so all of the large calculations that we run, he's the one that does them. So this is the four of us, and of course we collaborate with a lot of people over the world. Kadi and I have been, golly, how many years has it been? 20 or so? Anyhow, okay. I'll touch on some of these things briefly. I won't go through all of the slides, but we'll talk about global models and local models, and some of the advantages and disadvantages of both. Dick and I are strong proponents of global models, and we'll get into what that is, talk about how to create one and give you an example or two, and show you some applications of global models. So a global model is one that's created using a whole database. So for instance, and this slide is maybe a little bit old. At this point, the Scopus database has about 60 million items in it from 1996 forward. And the things that they've indexed further back in time put them closer now to probably 90 million indexed items. And PubMed, for instance, which covers the biomedical literature and some other stuff that makes it in there, is about 30 million indexed documents at this point. So a global model, when we talk about that, means that we're going to take the entire database and slice it up into a bunch of groups, things that could be called topics or disciplines or simply research clusters. Sometimes we talk about research communities or research clusters, but a global model takes the whole thing and partitions it at the same time. A local model, by contrast, is what almost everybody does. And so a local model is typically where somebody goes to the database provider of their choice, whether it's PubMed or the Web of Science or Scopus or Dimensions or any of several others, and does a query, oftentimes based on a set of keywords. And they say, okay, this is my data set on, epidemiology, just to take, one word. Or this is my set on graphene, or, and so it's based on a keyword search. Sometimes it's based on a journal or a set of journals. Now, the local model is quick and easy. There's software available to create maps from those local data sets. And that's when Kadi talks about anyone can map. That's the way it's done. It's done using these tools. Scitu is another tool that does that type of thing. The global model, there's not a tool out there that creates a global model for you. You basically have to use a suite of things in order to create a global model. And so there's a large upfront investment. The thing that's really nice about it, though, is that once you've created that global model, you've got everything in it. And so you can look up things, and you don't have to create lots of different local models for different situations. You simply find the pieces you want in the global model. So I'll just mention a little bit more here about a local model. And this is in preface to tell you about some experiments that were run. One of the local models that we worked with a few years ago was a model on astronomy papers. And so somebody defined a data set. It was based on about 60 journals over 8 years. and it had 111,000 papers in it. And these were all supposedly about astronomy because the journal set was based on an astronomy category of journals, okay? So I'll jump into that in just a little bit, in just a couple of minutes, and show you a comparison. Now, a question that one might ask, and this exposes our bias. I asked the question, why are global models more accurate than local models? That's an assumption, but it's an assumption I believe is true. And I'll show you a couple of examples. So here's a conceptual example. Let's say this represents all of the papers that are out there. And if you were to cluster all of those papers, they'd group into clusters like this. Okay, that's your global model. Now, let's say you run a query. You say, let's find all of the astronomy papers. And so you get all the astronomy journals and find those papers. And this little graphic represents where those papers are. Okay, well, if we take just those papers and cluster them, we get something like this. But if we go back to our global model and find where those papers are, we get this. Now, in some cases, those astronomy papers are together in both. Okay, if you look at the A's are together in the global model and they're together in the local model. That's cool, good. But then there are cases where things are grouped together in a local model that are not grouped together in a global model. And we find that happens almost all the time. So from a local model perspective, if you take your 100,000 papers on astronomy, what you're going to find is that the papers that are strongly linked within that data set, they cluster pretty well. But it turns out that there are a lot of less relevant papers that are included that don't cluster very well, but they get stuck somewhere because they're in the set. They didn't belong in the set in the first place, but they get put in a cluster because they're in the set. Also, there's a lot of papers that are missing from the set. And so with a local model, you don't know what you don't know, because if you don't know what's missing, you don't know what the recall is. And if you don't know what's irrelevant, your precision is low. So I'm going to kind of gloss over this. We actually ran an experiment. There were several teams involved where we all took this astronomy data set and everybody clustered it their own way. So, and there's a special issue in Scientometrics that has 7 or 8 papers in it and has the results of all of these different clusterings of the same data set. And the idea was not to try to figure out which one was best. The idea was to try to figure out why they were different. And we didn't exactly get there. But what we found, at least, and I should mention that instead of clustering those 110,000 papers, we simply looked them up in our model. And one of the things we found is that there were some groupings that were very similar to the groupings that were in some of the local models. You can see the dots on the upper right of this chart. When we had papers that had a high fraction of their links within the set clustered very similarly to what they would have done with just 110,000 papers. But then there were papers that only had 5 or 10, 15% of their links within the set, and they didn't cluster they clustered very nicely for us, but we didn't feel they clustered very well in some of the other sets. And this shows you some of the differences. So for instance, if you look at some of the papers in this astronomy data set that were about, so let's take this cluster 104 in the middle. The astronomy papers themselves were about 3 body problems. If you include all of the rest of the papers in Scopus and do your clustering, you find out that it's really part of a mathematics cluster rather than part of an astronomy cluster. So if you look at this bottom middle, the word cloud associated with the cluster those papers were in was all about mathematics. The other thing we found is that there were, in our models, there were lots of other papers that were astronomy related, but that weren't included in the data set. And this just gives a listing of 9 journals with tens of thousands of papers that could have been part of that data set, but weren't. And so the question is, if you're trying to get a picture of what's really going on in science and you're missing this much, is the picture you're generating from a local set really a good picture or not? Okay. I'm going to go ahead and jump past this. Somebody else did go back and do an evaluation, and it turns out that using the measures they evaluated these things with, our lookup seemed to be quite a bit more accurate than any of the other models. So this was kind of an independent evaluation that showed that the global model was actually better than any of the local models. Okay, to summarize global versus local, and please feel free to ask questions about this. In fact, I had to look at the chat and see if there's anything in there. Okay, it looks like, right, okay, that's Henry's paper there. So the global model, it's complete. You get full coverage, and so everything gets put in the global model, and this gives proper context for each of the documents. It's more accurate, at least we feel it is, and we feel there's good evidence for that. And if something's more accurate, you would assume it leads to better decision making. The global scale means that results are more generalizable. I see a lot of papers where somebody takes a small data set and they do something with it, whether they create a metric or whether they create a map, and they say, okay, this did this, which means that this is true for all of science, and that's just baloney. So the global scale means that the results are actually much more generalizable. Now, the other thing about a global model is you can include all kinds of stuff in it that's not in the database. So non-indexed content, if it's cited or if it links to your data, you can put it in this model. And I'm not going to go into all the ramifications of that, but it's really cool because you can link grants and you can link patents and you can link newspaper articles and policy documents, all kinds of stuff to the maps. Now you can do that a little bit with a local map as well, but of course it's not as comprehensive. Now, the local model, its great benefit is that it's quick and easy. And when it comes to the real core of the local model, it does a decent job of telling you what's going on. It does a really lousy job of telling you what's going on in the periphery. And unfortunately, the periphery is where all the interesting stuff happens. If you're looking for emergence, it's in the periphery, it's not in the core. If you're looking for disruption, it's in the periphery, it's not in the core. So we're strong proponents of global models. Okay, let's see. Now, let me step back and kind of answer the question, how would you make one of these things? Now, historically, this could only be done with Web of Science data or Scopus data. Today, it can be done with a lot more data sources, including open source data. And so I'll use PubMed as an example, with the caveat that PubMed is not fully global because it covers almost none of the physical sciences and engineering. It covers a little bit, but not very much. So if you think of biomedicine itself as being kind of a global, huge field, PubMed does a beautiful job with that. So the process of creating a global model is this. First of all, you have to gather your document level data. Now, if you're working with PubMed and 30 million articles, that's a lot of data to use, but it's available. You have to learn about and understand your data source. And this is true whether it's a global model or whether it's a local model. You need to understand what your data can tell you. If for a local model, if you're if your data set is based on keywords, you need to understand what might be missing, and you need to understand what you might have in there that doesn't belong. Those are the limitations. In a global model, those limitations aren't there, but you need to understand the limitations of the data source. I can give you perhaps one example. If you use something like Crossref or Microsoft Academic, you need to understand some of the additional data types that might be in those things and how those might cluster together and actually modify the way that the clusters look. So knowing something about the data is really, really important. Okay, the next step is to determine how to, what type of measure you're going to use to say how related pairs of documents are. And there's a lot of different ways to do it. Some people use keyword co-occurrence. Some people use a text-based measure using titles and abstracts. Others use citation links. Others use second-order linkages. And then there are different formulas that can be used. So determining which similarity measure you want to use is the next step. And then you've got to calculate this. And we tend to use the citation links because it's tractable. If you have 60 million documents and you're trying to do a textual-based similarity, the calculation is enormous. It's larger than what we can really handle very easily. And then we have to determine which clustering algorithm to use. And there are multiple clustering algorithms out there. If you're dealing with tens of millions of documents and with over 1 billion linkages, there are only a few choices. And it turns out that the Leiden algorithm is a very good choice. At this point, it's a modularity-based code, and it'll easily handle 60 or 90 million documents and 1 billion or 1.5 billion edges, linkages. Okay, once we've done the clustering, we can calculate cluster level information, and we can then visualize the results if we want to. And of course, places and spaces and all of this stuff we've been doing over the past 2 decades is about visualization. But what I would say, the visualizations are fantastic. But let's not get stuck on the visualizations. To me, the visualizations are an entry point that give me hypotheses about the data so that I can go look at the detailed data to try to answer questions. So for me, the visualization isn't the answer. The visualization is an entry point. And the data are what is really key once you drill down. Okay, for each of those pieces of the process, we now have choices to make. And I mentioned some of those in the last slide. So I'll just briefly mention here. Let's take PubMed as a data source. The unit of analysis is we're going to choose documents. So we're going to make a map of documents. Full database, we're going to go back 20 years or so. We are going to typically use direct citation. Those are the citation linkages. And then sometimes we'll add a text-based similarity. Now, another thing that can be done is we can threshold. We can threshold the linkages. It turns out that keeping all of the linkages often does not create a better map. The top 15 links per document is usually sufficient to give you a map that is quite accurate and very interpretable. That's something we could spend a lot of time talking about, and I won't do that here, but thresholding your links is really, it cuts down the size of the calculation, makes it much faster, and it's actually better. We use the Leiden algorithm, and then for layout, there are, again, lots of choices here, but we tend to use OpenORD. I know that TSNE is kind of on the rise, and a lot of people are using that now, and it tends to do a very nice job as well. Okay, so I'm going to jump. These slides that I'm skipping through were about a model from Scopus, but I'm going to jump to our PubMed model and talk about it. And the reason I'm going to talk about it is because we have open sourced this model, which means that you can go and grab the data, and you can grab an Excel file with all the information in it. You can grab a Tableau file also that has the map and the cluster information in it, and do your own analysis. So this is something that anybody can go and download from the web and use. So 3 main steps here. Each has some sub-steps. First of all, we created the model. And you can see that process. I'll go into it in just a minute in a little more detail. Then we characterized the model. So once we had generated our clusters, we went in and characterized the clusters. And once we'd done that characterization, we said, oh, well, we really need to make this accessible to people. And so let's put it in a couple of tools so that people can actually get at it and do real analyses. Okay, for the creation, we used over 18 million PubMed documents. We didn't go all the way back to 1900. We went back to, like 1996, I think, and just took the last 20 or so years worth of documents. Now, it turns out that in the past, PubMed did not have the citation links, but over the past few years, there have been a couple of organizations that have found the open source links and that link to PubMed documents and have made those publicly available. So those 2 sources are the Open Citation Collection at NIH and the Open Citations, which is a group in Europe that take Crossref data. And so between the 2 of those, we were able to identify 317 million, hey, that's a lot, linkages between these papers. Now, we had done some work where we said, we know that not all of the PubMed documents are linked because some of them are in open source, and so we don't have the citation linkages for them. But PubMed also has something they call their similar article scores. If you go to a PubMed page on the web, you'll see over on the right-hand side, there will be this thing that says similar articles, and it'll list a few. And that actually goes back to a database that NIH calculates and then they keep, where they have the top 100 similar articles for each article that's in PubMed. And so we have systematically mined those data over the years. And so for these 18 million documents, we took the top 20 similar articles for each one based on this textual based score. And so now we've got over 600 million links. Half of them are based on the citations and half of them are based on the text. So it's a hybrid type of situation. Now you'll notice that we have 317 million citation links and 314 million text links, and there's only 602 relatedness pairs. The reason for that is that there were almost 30 million that had both a citation link and a top 20 text link. Now let's think about that for a minute. Only 10% of the citation links were to papers that were in somebody's top 20 text-based list. So there is some overlap between the citation and the text signal, but it's not very large. That's just one kind of an aside, but something to keep in the back of your head. The citation and the textual information give you pretty much distinct information. There's only a little bit of overlap there. Okay, so we took our 602 million linkages and our 18 million documents, and we clustered it using the Leiden algorithm and ended up with almost 29,000 clusters. And then we used OpenORD and we created a visual map, and you can see a little picture of that here. So at this point, we now have our documents, and we have each document assigned to a cluster, and we've got a visual map of the clusters. Then the next step was, okay, I want to know what's in each cluster. I want to know what the clusters are about, because that's the actionable information. If somebody's at a med school and has questions about, what's my portfolio look like? If say a dean of a medical school, what's my portfolio look like? I need to be able to look at that at the cluster level. And it gives them all kinds of information. So we characterize the clusters using a bunch of other data. So we did simple things like, what are the top articles in each cluster? What are the top phrases in each cluster? What is the distribution of mesh terms and journals and categories and so on? But we also did things like taking STAR Metrics project data. These are NIH and NSF grant data, and using data from, NIH Reporter and STAR Metrics, you can link grants to particular documents. These are the documents that reference a particular grant in their acknowledgements. And so we can assign grants to papers and to clusters. And we can take the funding amounts associated with those grants and split it up among the papers. And we can tell you roughly how much money from NIH went into a particular cluster. So we added that type of information. We can also take patents and say, what science are the patents referencing? And we can tell you how many, fractionalized things, but we can tell you how many patents were associated with each cluster and how that changed over time. And so there's all these things that we do to characterize the clusters. We also look at things like industry involvement, because from the address data associated with the articles, we've got a list of, you can look for things that show you that either it's a university or a company. And so you can find the clusters that have a lot of industry involvement. You can find the clusters that have clinical involvement for looking where particular entities publish, hospitals and clinics and things like that. So there are a variety of other indicators that we calculated as well. But now we have a characterization of each of those 28 or 29,000 clusters. Patty will have these slides, so and this stuff's in a paper, so I'm not going to spend much time here on the data sources. Now that we've got our papers, each paper assigned to a cluster, we know what each cluster is about. We have all of this information about each cluster. We started putting all of that information, cluster level data, into an Excel workbook. And then we were working with somebody at University of Michigan, and he says, hey, I'm really good with Tableau. And so he took all of that information and put it into a Tableau workbook. And that means that we can now access all of that through the map, okay? And there are some other views as well. This slide shows you the DOI for those data. So somebody can go to this link here, this DOI, and download the Excel file and the Tableau file, and you can get Tableau Reader and start playing with it. But let me just take you through a little bit of what something like this can do. So here's a Tableau view, and these are our 29,000 clusters. And the cluster size, you can see with the various sliders over on the right and some of those fields, that the node size here is based on the number of papers. So the bigger the circle, the bigger the cluster. Now we're coloring the clusters by something called research level. And what the research level is it's a metric that shows you where on the basic to applied spectrum the particular cluster is. And this is based on some journal categories that were built years and years ago. In this case, red is basic and green is applied. So you can see that in this map, the red clusters are where your real basic science is occurring. The green clusters are where it's far more clinical, given that this is PubMed. And we can change, we can color based on a bunch of different fields. And then you can see there's a bunch of sliders here so that we can filter and look at particular sets of clusters. So let's just say now We also loaded into this database. At the time, there was a database called Cord19, and this was something put together by Allen Institute and some others. And it listed COVID papers. This was from about a year ago. And so what we did is we said, okay, let's filter and only show the clusters that have at least 20 papers in this COVID literature data set. So now we're down to just a few hundred clusters. Most of them are in that grouping right down at the bottom of the map, but there are clusters all over the map, which is interesting. It turns out that many of those clusters were associated with some of the basic research on proteins and so on that are part of the spike protein. Some of the others were associated with comorbidity factors and so on. Now, if we take our mouse and put the mouse over a particular cluster, we get a little window that pops up. And you can see, for instance, that the top phrase in that cluster was about SARS and SARS-CoV infection. And then it listed a bunch of the other metrics associated with that cluster. Now, that's just with a mouse over. If we click on that cluster, then we get another worksheet that pops up in Tableau, which lists the top phrases in the cluster, the top idiosyncratic phrases, which is, it's taking the top phrase list and rescoring it based on whether that phrase was prominent in other clusters or not. So phrases that were dominant in this cluster and occurred in very few other places rose higher in the list. You can also see at the top right the history of the papers in this cluster. So you can see that this cluster peaked in 2004 and 2005. This was a cluster about the original SARS rather than the COVID from 2019 and 2020. You can see top mesh terms, top journals, top categories, and then we also listed central papers. And if you scroll down, we listed review papers and then some of the metrics associated with the cluster. So this gives you a feel for how one might access a global model. All right, and this was the team that worked on this. We actually had an SBIR award from NIH, and some of that went as a subcontract to John Ioannidis and some of his students at Stanford. They worked on transparency indicators. All right, so let me jump to another couple of things here. Global models in practice. So you can download ours, the PubMed model, but there are some other things out there that are based on global models. So for instance, any of you who might have access to the SciVal tool from Elsevier, they have a feature in that SciVal tool, and SciVal is a competitor to Clarivate's Insights. So it's a research evaluation tool. It's based on Scopus, but they have a feature called Topics and have had for about 4 years now. And it's based on the way we do things. And also Insights recently launched their citation topics. The SciVal topics, they have about 96,000 topics in their set. I can see you've put the Georgetown map in there too, Kadi. I'll get to that in just a minute. Insights just launched their citation topics, maybe a year ago. And if I recall, they have about 2,300 clusters in theirs. Now, the Leiden ranking is also based on a global model. They have created a model using the same methodology. We're all using the same method here with some little twists, but it's pretty much the same method. But the Leiden ranking is based on their global model with about 4,500 categories in it. And then there's the recently released CSET map of science. And that's the one I think I'm going to mention first here. Okay, the CSET map of science, and Kadi put the link in the chat, is something you really ought to go try. it's a little, it's different from any of the others in that they have actually merged 4 different databases and tried to disambiguate papers across those 4 databases. So you've got the Web of Science, you've got Dimensions, you've got Microsoft Academic, and then CNKI, which is a Chinese language literature database that very few people have access to. But CSET is a Georgetown institution that stands for, it's the Center for Security and Emerging Technologies. And so they're aimed at being able to influence policymakers in Washington. And China, of course, is very much on the radar for people in Washington. And so they have access to this Chinese literature database and have linked it in and included it in this map. And it changes things to include the Chinese language. If you've got about 10 million documents from that Chinese literature database, it changes the distributions of things to include them. Let me switch over here. This is the CSET map of science. Okay, this is go to the web page and you'll see this is their map, and they've created it using direct citations. Among all of these things, there's about 110 million papers in it. They have over 100,000 clusters, and you can see that if you just scroll around the map, cluster number, and then they have information that's popping up over on the side that gives you a sense of what that cluster is about. You can click on a cluster and it'll pop up a new web page that then tells you what that cluster is about. And so the cluster subjects, these are the Microsoft academic subjects. So you've got level 1, level 0, 1, and 2 subjects, terms from Microsoft Academic Graph. They also do some extraction of terms from papers. And then they list various other things as well. They've got neighboring clusters. If you come over here and click on papers, it will show you some of the most central papers in the database. It'll give you some of the key authors and sources. And then if you come over to countries and organizations, it will show you some of those distributions as well. So the CSET map is pretty cool. You can also do some filtering here. So let's just say you wanted to look at NLP, for instance. So if we click here, if we type NLP into that filter box as a subject, now it's going to show you just those clusters in the map that are on NLP. And once again, we can go down to whichever cluster, and we can just kind of look at things and get a sense for who is doing what. And click on a cluster. Once again, here's some information about that cluster. So I just wanted to show you that this is a publicly available tool. Anybody can go to this website and look around at this map and use it for their purposes. The one thing that's missing is that there's not a listing of every paper that's in every cluster. I don't know if that will be made publicly available or not, because they are using a couple of commercial data sources in the map. Okay. Let me see how much time we've got. Well, okay, I think maybe at this point, I'll go back to show you just a bit about what it looks like in SciVal. So this is the Elsevier tool, and it uses the same methodology once again. And since they have institutions figured out in SciVal, you can actually go and look at portfolios for institutions. So for instance, if you wanted to understand what's going on at National Taiwan University, you would pick them out, and you can see that their scholarly output over a period of time was 37,000 articles. And there was a distribution of articles across these fields here. These are the Scopus subject categories. Now, if you want to just say, okay, let me look at medicine. Let's take the medicine category and take the top 5% of clusters that NTU is contributing to. And when I say top 5%, there's an indicator called prominence that they use that's basically a momentum indicator. So let's just say that let's look at the clusters in medicine, the top 5% of clusters in medicine where National Taiwan University has any publications, and these are the top 5% momentum clusters in the world. This is what that map looks like. And in this map view, they've taken the map and translated it into a circle. They've taken their 27 high-level subject categories, ordered them around a circle. And it's a pretty good ordering. You can see you've got math, physics, chemistry, chem engineering, materials engineering. It moves around into the biologies and into the medical sciences, and then through the social sciences, back to computing, and then math again. So it's a reasonable ordering of fields. And then they simply triangulate the position of each cluster based on the papers and the journals that they're in. And so you can get a quick sense of kind of the profile, the portfolio of a particular institution or a person or a group of people or whatever kind of a group you might want to define there. So if we take and look at the list now instead of the map, we can have, we see a list of topics, and we can show which ones they're a key contributor in. And a key contributor is a, they have to be either within about 1/3 of the highest output in terms of institutions, or they have to have a citation impact over a certain amount. There's some criteria that you use, but then you can take any one of these things and click on them and then go look at that particular topic. And you get a word cloud for the topic, so you get a feel for what that topic's about. And you can drill further. Well, I'm not showing it here, but then you could look at which institutions and which people, and with it being based on Scopus, you can actually go right down to the paper level to get an understanding of what's happening in this particular topic. So, okay, this is from a different talk, so I don't think that's as applicable here. I'll just summarize a couple of things here, some points. Back to global models, we feel they're more accurate than local models because local models can contain irrelevant papers, they can miss key papers. We feel that analyses of global models lead to more accurate results, but they're not everybody has one. That's why we've made our PubMed model publicly available. The CSAT model is now out there, and others may be coming in the future. But they do require a lot of investment up front to create the global model. But once you have them, of course, you can do all kinds of analyses with them. Now, visualization of global models is very elementary at this point. You can see what we've got. We've just got scatter plots. We've got map plots. And so additional visualization development would make them even more useful. Here's some references. Again, these will be in the slides that get sent to Kadi and posted. And with that, I will quit and quit sharing my screen. And there's 10 minutes left for whoever wants to do what. And Kadi, if you just want to fire questions, that's cool.
Thank you so very much. It's cool to see this evolve over the years. It's just amazing what has been done. So again, audience, feel free to also ask questions. My question for you, Kevin, is what are the next projects you will be working on? And then also, how do you decide which project to work on? Because there are so many opportunities to use these maps and to use the skills that your team has. And you always have to make a decision, right? So
Well, that's
which
true.
project, which
It's, yeah.
client do you pick?
So there are several actually that we're working on right now. One of the things I didn't get into, we published a paper about a year ago and we're updating it. We're working on the next iteration of that, and that is forecasting. So yes, we are actually forecasting. It's certainly not perfect. Nobody, historically, nobody's done a very good job of forecasting science, right? But it turns out there's some really good signals in the clusters that allow you to, to some degree of accuracy, say that this cluster is going to experience extreme growth in the next 3 to 4 years. And we're not bad at that. We're pretty good at that. Now, it's the major signal there is trend extrapolation. I mean, it really does get back to that. But the other thing we've found that is really fascinating is that above that, if you know what the types of authors are that are in the cluster, you can do a better job of forecasting. Okay. Now, when I say types of authors, what does that mean? Well, Dick likes to talk about foxes and hedgehogs. And I don't know if anybody's heard that kind of an example. A hedgehog has a home and they do one thing and they're an expert in one thing. And a fox usually has multiple homes, but not too many. I mean, but a fox is somebody who's an expert in more than one thing, and they actually spend time in all those things. Okay. And then we talk about birds, and birds flit around and they put their seeds everywhere, right? And so they've got a little knowledge about a lot of stuff, but they're not really totally expert in one or two things. Well, it turns out that the mix of those types of authors has a lot to do with where the topic is going to go in the future. So I'll let everybody think about that one for a minute. If you can characterize authors as a hedgehog or a fox or a bird, the mix of those people in a cluster is a pretty good indicator of where the cluster is going to go. And what it is it's the visitors, the experts. If you take the experts and you say, where are they visiting? Those places are going to pop. Those topics are going to pop. The experts, those people have a sense, they have a smell for science, and they visit, and then they start to inhabit the places that are going to pop, and we can show it numerically. So that's a new thing that we're working on that paper too. We are really interested in identifying which of the topics are based on social aims rather than economic or academic aims. And that's something we're really interested in, and nobody's done it well. So anybody who's got any ideas about that, send them our way. We've got a lot of ideas. We're chasing some of them, but trying to understand social aims, socially driven science. And part of the reason to do that and to do it well is because the entire incentive system, especially in academics, ignores it. Maybe not entirely, but mostly. And so if we can show where, which part of the map is based on social aims, and another thing we're seeing is that females are more heavily represented in the areas with social aims. And so this is something that is convoluted, it's a factor in the gender differences. What would that knowledge, if it was, if it went to funders and they took it to heart, do for the future? So those are the kinds of questions we're asking there.
I also have have seen other work which just looks at which areas of science attract younger authors, so just career age, when did they publish the first time and how old are they now in terms of the career age. And I think that's also a pretty good indicator. I also remember your work on the weavers and threaders. So some people just are going through science, and I guess that's kind of your hedgehog. And then there are those which are, or those are the threads basically of science. And then there are some which are just weaving all these threads together. I think these visual metaphors you and Dick have been communicating to all of us are very powerful, and I hope you continue to do it. And you do, because you just gave us a new metaphor of foxes, hedgehogs, and birds. That was a new one.
So yeah, that's kind of where we're going in the future.
Good. And so if you have to make a decision between two projects, which one do you pick? Because I think we have some younger career scientists here, and they need to make these decisions and say no, right? So it's a very important question in life.
It is. It's really an important question. And I can't say our criteria are the ones that anybody else should use. We tend to choose the ones we care about.
Mm-hmm.
Whether or not we can get any funding for it. We choose the ones that personally go, oh, I want the answer to that. I want to understand that. We choose those. We also choose, well, and both of us are pragmatic. And so we tend to choose the one that has the most practical significance. At the end of the day, which one has a chance of influencing policy? We'll take that one over the academic one anytime. I mean, we have, in the course of our investigations, we have so many things we've tripped over that would make a great academic paper, and we've never written the paper because it would just take time away from finding something that's useful.
But others can benefit. They don't have to redo it. I think you and Dick have been just really good in productizing what can be done and showing the world that this can be done at large scale, just like what Elsevier and Claret did as professional companies with thousands of employees. But it can also be done at a smaller scale, at a very innovative, agile scale. And I think I would love to see more of this, especially now that we are living in a time and age where COVID is changing and causing a lot of change. And I think Andrei Skupin actually has done some COVID maps, so we will get to see this next. So Kevin, thank you very, very much for coming in on a Saturday afternoon for you and evening for us here. It's a true pleasure to get an entire hour with you. I hope many get to benefit. And I hope we all see each other at the ISSI conference in 2023 here in Bloomington, Indiana. So I hope that this will be an in-person event, and there will be dancing as typical at ISSI conferences, and there will be lots of good conversation about how to improve the study of science by scientific means. Thanks so much also for being on the organizing committee there.